Hey everyone, in today's video we'll be looking at two interview questions, one fairly short one and the other a bit longer. The second problem we'll be looking at is called the gambler's ruin problem and is a famous problem in probability, so hold out for that. But for now, let's get started with the first problem. So for the first problem, we're asked to give the expected number of rolls of a fair die needed to get all 6 numbers. So have a think and I'll be right back with the solution. So we'll start off by defining 6 random variable x1 through x6, where xi just stands for the number of rolls to get the ith unique number. Given that we've rolled I minus 1 unique numbers. This should be in xi. So all the xi's are just define the number of rolls to get the ith unique number, given that we've rolled I minus 1 unique numbers, meaning that x4 is the number of rolls that starts counting right after we've rolled 3 unique numbers. And so why do we define it this way? Well, in this case, we know that xi's follow a geometric distribution. Geometric. And if you've never seen the geometric distribution, it's basically, it stands exactly for the number of trials you need to get a success. So the probability mass function is actually given by the probability that x is equal to k is equal to 1 minus p to the k minus 1 times p. So this just means basically that the first k minus 1 trials were a failure, and then this is a success. And so in our case, failures are getting a number that was already rolled, and then the success would be getting a new unique number. And so we can already see that for x2, for example, the probability of success would just be 5 over 6, since in 5 over 6 of the rolls, we'd get a new number, and in 1 over 6, we'd get the number that was already rolled on the first roll. And so this would actually follow a geometric metric with probability of 5 over 6. And then let's think about x3. Well, this is a geometric as well, but with probability 4 over 6, since now only 4 of the 6 rolls that we can get would actually lead to a new number. And so for all the xi's, we just have that this follows a geometric distribution with probability 7 minus I over 6. Okay, and so now we know that the mean of the geometric distribution, or the expectation, is just 1 over p, where p is again the probability of success. So for example, e of x2 would just be 1 over 5 over 6, which is 6 over 5. Same for e of x3. E of x3, this is just 1 over 4 over 6, which is just 6 over 4. So let's try to calculate the entire expectation now of 1 through 6. Okay, so the expected number of rolls to get all 6 different numbers is the expectation of the sums from I is equal to 1 to 6 of all the xi's, which is just the sum from I equals 1 to 6 of the expectations of xi's. And we already know the expectations of xi's, so this is just, we can actually write that as sum. This is just 1 plus 1 over 5 over 6 plus 1 over 4 over 6 plus 1 over 3 over 6 plus 1 over 2 over 6 plus 1 over 1 over 6. And this is actually just 14.7. So the expected number of rolls to get all 6 numbers on a fair dice is 14 over 7. Alright, let's try to run a simulation to confirm our answer. So we'll import random. We'll also define the number of rolls function. It takes just n as trials, and then we'll define the dice, or the die, I guess, to just be those 6 numbers, and we'll define the number of rolls to be just 0. Okay, and then we can just loop through the n trials for in range n, and then rolled, we'll just let this be an array, an empty array for now. We'll just add all the rolls we get to this array, and then we also say we'll also keep track of the number of rolls. And so we'll say while the length of this rolls are rolled is less than 6, since we want all 6 numbers to be in this rolled function, we'll just pick a random dot choice from those from that dice, and then we'll just also increment the number of rows by 1. And then we say if x not in those rolled, we'll just append that x. All right, and then out here we can increment the number of rows by the rows we have, and then down here we can just print expected number of rows. We'll just say number of rows divided by n. And so here we can just print another line, and then we'll say number of rows, and we'll run this for let's do 1,000,000 trials. Okay, and so if we run this, we get 14.7, which is what we calculated. Okay, so for problem 2, this is the gambler's ruin problem now. So it says that a gambler starts off with the initial fortune of $i, and in each instance of the game, the gambler wins $1 with probability p in the interval from 0 to 1, and loses $1 with probability just 1 minus p. We'll call this q. And then he will stop if he ever accumulates n dollars or loses all his money. And we're asked to give the probability that he ends up with n dollars. So have a think about it. It's really not an easy problem, so you might get stuck, but I'll reveal the solution in any case. Okay, so to start off, let's define PJ to be the probability of eventually getting n dollars or eventually winning at j dollars. So this is the probability of eventually getting n dollars at j dollars. And this is defined for all j between 0 and n. So now we can write pj is equal to p times p j plus 1 plus q times p j minus 1. And why is this? Well, p is just the probability that the gambler loses the first game. And then if he loses the first game, he'll be at j plus $1, which means that his new probability of winning is pj plus 1. And q is his probability of losing the first game. So his probability of winning would just be, since he loses $1, it'll be p of j minus 1. Now we'll actually rewrite this equation as, since we know that p plus q is equal to 1, we can actually write this left-hand side here as p plus q times pj, right? We just multiply by 1, which doesn't really change it. And then we can distribute this out to get p times pj plus q times pj. And so on the right hand side we still have p times pj plus 1 plus q times pj minus 1. And then if we take this term to the left hand side and this term to the right hand side, we get that q pj minus q pj minus 1 is equal to p times pj plus 1 minus p times pj. We can factor out a q here and the p there, so we get that q times pj minus pj. I don't know what this minus 1 is doing here. This minus 1 should be down here. J minus 1. And then here's p times pj plus 1 minus pj. And so dividing by p, we just get that q over pj minus pj minus 1 is equal to pj plus 1 minus pj. And we forgot a bracket here. Okay, so if we clean this up a bit, we'll just move all this business up here. And so now we can write pj plus 1 minus pj is equal to q over pj minus pj minus 1. All right, so we've just rewritten it. And actually now if we plug in, let's plug in 1 for j, sorry. That would give us that p2 minus p1 is equal to q over p times p1 minus p0. Well, p0 is just 0 since you already lost if you're at p0. So this is just p1 minus, or q over p times p1. And so if we do the same thing for plugging in j equals 2, we get that p3 minus p2 is equal to q over p times p2 minus p1. But now we already know what p2 minus p1 is. It's just this. So this is just equal to q over p times q over p times p1. So this is just q over p squared times P1. And actually, we can generalize this. We have that Pj plus 1 minus Pj is equal to Q over P to the j times P1. Okay, so if we clean this up again, we actually have a pretty interesting result here. We've related the probability of winning of j and j minus 1, or j plus 1 and j right here, just to the probability of winning at $1. So this is actually a pretty cool result, and we can use this to solve for the Pj. Okay, so this is an important result we'll use later, but for now, let's try to find the probability of j plus 1 minus the probability of 1. It'll become clear why we're looking for this. So this, we can just split this up into the Pj plus 1 minus Pj. We've subtracted Pj here, so we have to add it back. So we'll have Pj minus Pj minus 1. Here we've added back the Pj but subtracted a Pj minus 1. So we have to add it back. And we'll actually do this all the way down to P2 minus P1. So yeah, we've just expanded this this difference into the sum of a bunch of differences just by subtracting and then adding back. Here subtracting, and here you can imagine that we added this back all the way here where we subtracted P2 and then added P2 back here. And so this is just the sum from k is equal to 1 to j of Pj plus 1 minus Pj, which is the sum from k is equal to 1 to j of q over p to the k times P1, right? Using this formula right here. And so this is useful because we can now take this bit, we can take the P1 and add it onto the right hand side here to get that Pj plus 1 is equal to P1 plus the sum of k is equal to 1 to j of q over p to the k. This is a q, yeah, and then plus P1. So this is actually pretty cool. We've written the probability of j plus 1 for any j as just the sum of probability of p's, or sorry, of p1s. So if we know p1, we automatically know the p of j plus 1 for any j. And so here we can factor out a p1. This would just be 1 plus the sum from k equals to 1 to j of q over p to the k. And so here, note that q over p to the 0 is just 1. So we can actually include this 1 into our sum by just summing from 0. So this would just be p1 times the sum from k is equal to 0 to j of q over p to the k. Because when k is 0, q over p to the k is just 1, which is equal to this term right here. Okay, so we've arrived at our second important formula, which is exactly this one. We can clean it up and add it back. There we go. And let's circle this as well. There. And now we want to find a value for this part right here. If you can see, this is actually just a geometric series, since there's a common ratio of q over p, and whenever you have a common ratio in a series, it's just a geometric series. So there's actually a formula to calculate this value for any geometric series and ratio. So the actual formula is that if you have, let's just say, I don't know, k is equal to 0 to n of a times r to the k, where r is the common ratio, r is equal to common ratio, and then a is equal to, it's just the first value. Okay, and so in our case, the first value is just q over p to the 0, which is 1. Anything to the 0 is 1. And then the common ratio is just q over p. And so what is this geometric series formula actually? It's actually split into two cases. One is when the ratio is 1, and then one is when the ratio is not 1. So if the ratio is not 1, this is equal to a times r to the n plus 1 minus a over r minus 1. So this is if r does not equal to 1. And so if r does equal to 1, this is just n plus 1 times a, if r is equal to 1. So now we can actually split up our solution into two cases. One is where the ratio is 1, which means that q is equal to p, which means that they both have to be 0.5. So kind of the gambler's chance of winning and losing are the same. In this case, using this formula above that we calculated, we can see that pj plus 1 is equal to p1 times, well, the sum of this will just be n plus 1, or well, in this case, n is j, so this would just be j plus 1. And then since a is just 1, we know that, yeah, it's just p1 times j plus 1. And so here, if we plug in n minus 1 for j, so we'll have that j is equal to n minus 1. We'll get that pn is equal to p1 times n. And so from there, it follows that p1 is equal to pn over n. And actually, pn is just 1, since if you're at n dollars, your probability of winning is 1. So this is 1 over n. And so if we plug this value back in for p1 right here, we get that pj plus 1 is equal to, well, 1 over n times j plus 1. Which means that if we plug j minus 1 in for j, that means that pj is equal to j over n. And that's our solution if q is equal to p is equal to 0.5. Okay, so let's move our solution for the first case up here. You can just move this guy up here, and we'll put a box around it too. And we'll just say here, if q is equal to p is equal to 0.5. So this means if p does not equal to q, then we need to use this slightly more complicated formula. So in this case, we'd get that p of j plus 1 is equal to p1 times all this business right here, all this formula, which is just q over p to the j plus 1 minus 1 divided by q over p minus 1. And so we can again substitute j is equal to n minus 1 to get that pn is equal to p1 times, actually we don't even need this, times q over p to the n minus 1 over q over p minus 1. And so solving for p1, we just get that p1 is equal to pn times this whole fraction, which is q over p minus 1 over q over p to the n minus 1. Okay, so we'll clean this up a bit too. We're kind of running out of space, but that's all right. There we go. Okay, so now we can plug in our value for p1 into here. But before we do that, let's just notice a couple things. First, pn is just 1 as before, so we can cancel this term out. And then these two terms will actually cancel out because it's the exact same thing. So the answer then is that p of j plus 1 is equal to q over p to the j plus 1 minus 1 over q over p to the n minus 1. This is very ugly right now, so let me rewrite it here. P j plus 1 is equal to q over p to the j plus 1 minus 1 over q over p to the n minus 1. And so moving this over for a bit more space, in this case, all we have to do is plug in, I guess, I minus 1 for j, which means that pi is equal to q over p to the I minus 1 divided by q over p to the n minus 1. Okay, so this is our second solution in the case, so if q does not equal p. Okay, so that was a lot, and the answer isn't necessarily intuitive, so let's try to simulate this to get a better understanding of the answer. So we'll import random. We'll also define the gambler's ruin function, and this takes in 4 parameters, p, I, big N, and then little n. And let's define the variables here. So this would be the probability of winning. Then I would just be the money at beginning, and then N would be maximum money to win. So if he gets N dollars, he wins, and then N is just the number of trials. So we'll also define a variable to keep track of our wins. Then we'll loop through the N trials. There we go. And we'll say done is equal to false, and also money is equal to I. This is the money he starts, or the gambler starts off with, and we'll say while not done. And then we'll pick a random number, uniform from 0 to 1. And so if we want the probability to be P, we'll just say if X is less than P, or sorry, if X is less than P, then gambler wins. So we'll say money plus equals to 1. And so if X is bigger than P, or I guess we'll just say else, else. Then we'll say money negative equals to 1. Okay, and so if money is equal to 0, or money is equal to n, we'll say done is equal to true. And then down here we'll say if money is equal to n, I'll say wins plus equals to 1. Okay, and then down here we can just say probability of winning, I'll say wins divided by n, and we can add another line to make it look nice, and then we'll say gambler's ruin. Let's try an easy one first. Let's say the probability is 0.5. We'll have 3, 10, and let's do 10,000. Okay, so before we run this, note that since the probability of winning is 0.5, P is 0.5, which means that Q has to be 0.5 as well. So in this case, we just expect the probability of winning to be 0.3 because it's 3 over 10. So let's see if we get that. Yeah, we can see that that's exactly what we get. And let's try to run this with a different number here maybe, so 6. Let's try this again, and we get 0.6. Now let's try some different numbers. Let's try P to be 0.6. We'll have 3 at the beginning and then 10 at the end. And so we'll show it on screen, but right now this is expected to get about 0.716. So let's see if that's what we get, 0.716. And that's pretty much what we get. We can do a different one as well. Let's try 0.3 as the winning probability. We'll start off with 10 and then we'll have 15. And so this is expected to get about 0.014. And so let's see if this is right as well. 0.15, 0.14, yeah, seems to be right. Okay, so thanks for watching. I think this is definitely one of the longer problems we'll do on this channel, but I think it's important to know it since it is pretty famous and it's also a good practice in probability. So if you like this content, please consider subscribing and I'll see you guys next time.